Hey everyone. So for this lab, we are going to be talking about the formation of tetraphenylcyclopentadienone. So let's look back at our scheme for the synthesis of hexaphenylbenzene, our final product for the semester. So we started off by purifying benzaldehyde, and then from this benzaldehyde, we converted it all the way down to diphenylacetylene, which is one part of our, for the final reaction. And then from benzaldehyde, we've gotten all the way up to this molecule, benzyl. So now we're going to make the last reactant we need to make our hexaphenylbenzene by reacting our benzyl with this new molecule called dibenzyl ketone, or diphenylketone. So once we produce this molecule, we'll only need one last reaction before we get our final product. So this reaction involves a cyclizing double aldol condensation reaction. And so the way this works is here we have our dibenzyl ketone, and we're going to react it with a base, some kind of hydroxide. So the negatively charged hydroxide is able to come and deprotonate our dibenzyl ketone, and this forms this anion on the carbon. Once this anion forms, it can come and attack the carbonyl group of our benzyl. So you can see the negative charge comes in, but forms a new bond to our carbonyl, and this breaks the carbonyl bond, leaving a negative charge. From here, the negatively charged oxygen can reclaim the hydrogen that was first removed from the dibenzyl ketone in order to form an alcohol. So now that we've formed this alcohol, we can use this negatively charged hydroxide, or ethoxide, and it can come in and perform what is known as an E1CB elimination. So it's very similar to any elimination reaction you've already seen, but instead of it being a one-step, it's a two-step reaction. So what happens is, like the most elimination reactions, the negatively charged oxygen can come in and remove the hydrogen first, and this will actually leave a negative charge on the carbon. This negatively charged carbon can then come in and move over towards the other carbon, and in doing so forms a double bond. And in this formation of a double bond, it'll kick out the hydroxyl group, and what we're left with is this new molecule. So you can see the final product is the exact same you would expect from an elimination reaction, where we've removed a hydrogen, formed a double bond, and had the hydroxyl group leave as a leaving group. So the next couple steps are the exact same thing, where we're going to have some kind of base come in and remove this hydrogen that was on our dibenzyl ketone and give us a negatively charged carbon. This negatively charged carbon can attack the other carbonyl group that was in our benzyl and form a new bond. And here you can kind of see we now have a cyclic penta structure. And just like we saw with the other elimination reaction, we can do it here once again. So first, the negatively charged oxygen comes in and reclaims the hydrogen to form an alcohol, leaving us with our base again. And then this base can come over here and remove this hydrogen. From the removal of this hydrogen, we're left with an anionic charge on this carbon. The anionic charge can move towards the next carbon and form the double bond. And in the formation of this double bond, we kick out the hydroxyl group. And once this happens, we have formed our final product, the tetraphenylcyclopentadienone. So really, it's a pretty simple mechanism where we're just doing the same reaction 2 times. You'll know that you've purified or made the tetraphenylcyclopentadienone because this molecule is deeply colored purple. And this comes from all of the pi bonds that are here that, because of this, gives it its purple color. Something to note is that the resonance of our final molecule is anti-aromatic. So if you look at this, I guess the 2 resonance forms, if we break the double bond into a negative charge on the oxygen and a positive charge on the carbon, what we're left with is a resonance form that has a 5-membered ring with 4 pi electrons, making this a 4n pi system, which is anti-aromatic. And so if something to note is anti-aromatic molecules tend to be more reactive, so this is going to be incredibly helpful for us in the final reaction when we want to make our hexaphenylbenzene. So to perform this experiment, it's a 1-pot reaction where we throw everything we need into a 100 milliliter round bottom flask. So into this flask, we're going to be adding 1.05 grams of benzol, 1.05 grams of dibenzyl ketone. We'll also be adding ethanol as well as potassium hydroxide for our base, as well as a couple boiling chips to help boil the reaction. We then attach this to a reflux condenser, and then we just bring it to a gentle boil and let it boil for about 15 minutes. The increase in temperature is what's going to help drive this reaction, and you will slowly see the reaction go from clear to purple, which will signify that we've made our final product. So remember that the mixture will turn a deep purple color, which signifies the formation of tetraphenylcyclopentadienone. Once you see this purple color and you've just let it go for a couple minutes longer just to make sure as much of our reactants form the product, you would then take the mixture and then cool it to room temperature using an ice bath. Once the reaction cools, you'll see that you'll form some crystals, which you can separate using the Buchner funnel. Once separated, you just wash these crystals with some water and cold ethanol and just allow it to dry. And from here, you have your final product. You can then weigh it in order to calculate the yield, as well as check the melting point to make sure that you actually purified your final product. So tetraphenylcyclopentadienone should melt around 218 to 220 degrees Celsius. Some other considerations that other than the product having a deep purple color, we won't need to recrystallize anything. Like, it's not really necessary. And in terms of safety, the most important, or I guess the most dangerous chemical that we'll be working with is the potassium hydroxide. So potassium hydroxide is a very, very strong base, and because of this, it can cause some serious chemical burns, not only as if it were to be as a solid, but also when it's a liquid. Well, so let's try to calculate the theoretical and percent yield of the tetraphenylcyclopentadienone when we're starting off with 1.05 grams of benzol and 1.2 grams of our dibenzyl ketone. And once we've completed the entire reaction and purified our product, we've isolated 1.7 grams of product. So because we have 2 molecules that could be the limiting reagent, what we need to do first is actually calculate which one is the limiting reagent. So to do this, we need to calculate the amount of moles that each chemical is kind of contributing to the reaction. So for the amount of benzyl that we're using, we have 1.05 grams. We just divide it by its molecular weight, 210.23. And this gives us 0.005 moles of benzyl. If we do the same with our dibenzyl ketone, we take the 1.2 grams and divide it by the molecular weight of dibenzyl ketone, which is 210.27 grams per mole. And this gives us the 0.006 moles of dibenzyl ketone. So from here, we're able to conclude that our limiting reagent is the benzyl. We can then take the amount of moles of benzyl we have and try to calculate the theoretical yield of how much we should have of our final product at the end of this reaction. So for this reaction, we take our 0.005 moles of benzyl, and we're going to try to convert it to the tetraphenylcyclopentadienone. So we saw that from the reaction mechanism, for every 1 mole of benzyl, we're converting it to 1 mole of tetraphenylcyclopentadienone, or TPCPD. So to convert a mole of TPCPD, we just multiply it by its molecular weight, which is 384.5 grams. So in the end, the final calculation is 0.005 times 384.5, which gives us a final mass of 1.92 grams of TPCPD. So we should expect, if everything in this reaction went flawlessly, we should expect to have exactly 1.92 grams of our final product. But after performing the experiment, we only isolated 1.7 grams. So what is our actual percent yield? To calculate this, we just take what we isolated and divide it by what we thought should have been isolated, so 1.7 divided by 1.92, and then multiply it by 100, and this will give us 88.5%. So this is the final percent yield that we were able to isolate. Now let's take our final product and analyze it using IR spectroscopy. So here is our molecule. When we look at this molecule, there are only really a couple functional groups that we could easily see. So we can see we have a lot of aromatic rings, each of which have an sp2 hybridized hydrogen. So we should expect to see something above the 3000 wave number mark, which is right here. And then for our second functional group, we can see that we have this carbonyl that should show up around the 1700 mark, which we can clearly see right here. So the IR spectrum does definitely show us what two major functional groups we should be seeing. And just to really make sure, we can also analyze the NMR. So what makes the NMR a little bit more difficult to analyze is we only have hydrogens on our phenyl rings or benzene rings. And so because of this, this means most of these rings or most of the signal is going to be locked in this 7 range. So we can expect that most of these hydrogens belong to these peaks that you see right here, and it's really difficult to distinguish them. So you can see that we have one group of peaks above 7 and another group of peaks below 7. So while all of these peaks have to or involve the hydrogens on these benzyl rings, we can kind of guess or assume that this singular peak that we have here might have to do with hydrogens that are closer to our carbonyl group, because these hydrogens will feel less of an effect than the hydrogens on these rings. So for this peak here, we can try to assume that they might belong to these hydrogens here, so the ones closest to our carbonyl group. So let me draw those out. So these hydrogens here, because they are the closest ones to our carbonyl group, I would expect to form this peak right here. And then this peak would be made up of all of the hydrogens that are left over. So these, all of these. So from this NMR, this is what we can expect our final product to look like.